about scientists discovering planets 300 or 400 light years away from Earth. However, the question arises, how do astronomers determine that distance? Measuring the distance from us to stars and galaxies in the universe has always been a great challenge. Even with the most modern equipment available today, modern astronomers have powerful tools to observe stars and galaxies, such as the recently launched Space Telescope, but there is still no optimal method to accurately determine the distance between us and a star or galaxy. Below are the methods that astronomers use. The first method is triangulation. Scientists know that Earth's orbit around the Sun has a diameter of 300 million kilometers. They use a telescope to observe a star on one day, then observe it again after 6 months. Astronomers rely on 2 observations when Earth has orbited half a circle around the Sun to draw a triangle with the star to be measured at the vertex. The base of the triangle is 300 million kilometers long. By determining the viewing angle from Earth to the object and the difference in light between the 2 observations, they calculate the distance from Earth to the star. The unit of measurement for distances between stars is the light year. However, the triangulation technique only applies to objects about 400 light years away from Earth. The second method is parallax. This is a common method for nearby stars in our galaxy, ranging from a few hundred to over 1,000 light years from the solar system. Astronomers select a star near Earth as a reference, then use a telescope to observe the target twice, similar to the triangulation technique. Data from the observations helps them draw 2 triangles with a common vertex at the star. Astronomers use trigonometric methods to calculate the distance to the object being measured. For the Moon and some nearby celestial bodies in the solar system, calculating parallax is quite simple and quick. For example, the method of calculating parallax to determine the distance to the Moon is as follows. 2 observers equipped with telescopes observe the Moon from opposite sides of Earth. Their lines of sight are represented by dashed lines, along with a solid pink line representing the distance between them. His line of sight deviates at an angle from observer A due to the parallax principle. The angle formed at point B in the triangle is called theta. When the Moon moves into observer A's line of sight, observer B adjusts the telescope to aim at the center of the Moon. Then, observer B measures his angle theta. In practice, he aligns the image to point at the center of the Moon. Then, observer B measures the angle theta with a protractor, similar to a rangefinder. Once the angle theta value is determined, it is used to calculate the distance r between Earth and the Moon, using the same equation as with the rangefinder. The only variable to determine before measuring the distance from Earth to the Moon is d, representing the distance between the 2 observation locations on Earth. This parallax method has been known for a long time, and ancient Greek astronomers also used it. The annual parallax method is widely applied to stars within a few hundred light years, sometimes even to stars more than 1,000 light years away. With modern telescopes, humans can apply the parallax method to detect planets at distances up to 10,000 light years. However, for galaxies that are too far, astronomers cannot calculate using triangulation and parallax methods, but instead use a brightness technique based on the light spectrum emitted by the star. For distant stars or other galaxies, the parallax method based on viewing angle changes cannot be used. Astronomers use another method called spectroscopic parallax, which relies on the deviation obtained from the star's spectrum to determine the distance. Based on color, experts can determine the actual brightness of the object, then compare it with the light of a standard star to calculate the distance to Earth. This technique helps identify objects hundreds of millions of light years away from Earth. The Hertzsprung-Russell diagram is used to classify stars in the universe based on their spectral colors. From the spectral color and comparison with this diagram, one can know which group a star belongs to and relatively accurately determine its absolute brightness. Absolute brightness is the brightness of any star when observed at a standard distance of 10 parsecs. Therefore, this brightness does not depend on the distance from the star to Earth. To determine the spectral parallax of a star, one compares its absolute brightness with its apparent brightness. The apparent brightness is precisely the brightness of the star that we see every night in the sky, and it depends on distance. Stars in a galaxy are at different distances from us. If two stars have the same absolute brightness, the more distant star will have a smaller apparent brightness. By comparing these two brightnesses, astronomers can determine the distance of the star. For galaxies, the spectral parallax method is performed differently, based on Cepheid variable stars. Cepheid variable stars are stars located on the main sequence of the spectral. They are old stars that have reached the final stage of their lives, with very strong brightness variations. Astronomers observe their brightness variations in a galaxy, from maximum to minimum brightness. Their variation period indicates the absolute brightness of the star. This comparison is more complex than measuring the individual distance of a single star, because astronomers need to relatively accurately estimate the total number of Cepheid stars in a galaxy and their total brightness. Typically, this method is applied to relatively nearby galaxies, specifically those in the local group. For galaxies or galaxy clusters that are too distant, accurately estimating the brightness of Cepheid variable stars becomes very difficult. Astronomers use another observational object, type Ia supernovae, explosions of stars at the end of their life cycles. Because supernovae have much greater brightness than variable stars, determining the brightness of supernovae is much easier for relatively distant galaxies. What about galaxies that are very far away? Welcome to Hubble's law. This is currently the most common method for measuring distances to distant galaxies. In 1929, Edwin Hubble discovered the recession of galaxies through the redshift in their spectra. This discovery led to the conclusion that we live in an expanding universe, accompanied by Hubble's law regarding the recession velocity of galaxies relative to us. The formula of this law is as follows. V is the recession velocity of the galaxy, h is the Hubble constant, and r is the current distance of the galaxy. The Hubble constant has now been relatively accurately determined because it yields computational results that are very consistent with results calculated from observations of the cosmic background. The velocity v can be calculated by tracking the redshift of. From that, one can immediately calculate the distance r of the observed galaxy. This method using Hubble's law is widely applied in measuring distances to distant galaxies. However, it is not applied in cases using parallax and spectral parallax, because nearby stars do not exhibit recession motion according to Hubble's law. And galaxies that are too close have quite small redshifts, making accurate determination difficult. In general, methods for measuring distances in cosmic space are quite complex, requiring deep understanding of trigonometry and light spectroscopy, along with the support of modern instruments like telescopes.